Perfect.
And we should also do it.
Are you connected?
Everything under control. Got everything under control.
All right. Welcome to day 2 of Inter+Stellar, folks. I had so much fun yesterday. I hope you did too. Sorry, I came up here a little late because I was so distracted by all the cool science that was happening in the cafe. But we are ready to go. So, ready to go? And we'll get going.
Good morning, everyone. My name is Christina without H, and my research typically focuses on optical and near-infrared studies of globular cluster stellar populations. But actually, I also have some interest for pulsar science. Actually, today I feel in between of these two research fields, and I'm going to present some results about dust and free electrons that we can obtain just putting together these two research fields. Let's start with a brief introduction about globular clusters. Globular clusters are gravitationally bound crowded stellar systems, and even if we know that is not anymore true, they still can be considered the best example of simple stellar populations. That means that they are made up of old, coeval, and chemically homogeneous stars. And thanks to these properties, if we study the color magnitude diagram of globular clusters, we can distinguish very well-defined evolutionary sequences. But what happens to these sequences if we locate them in different parts of our galaxy? First of all, if we move our cluster further, the evolutionary sequences become fainter. Then, if we add some dust in the middle, the evolutionary sequences become fainter and redder. And if we assume that this dust is spatially variable, we also have a broadening of evolutionary sequences, and they are not well-defined as before. But just rewinding these steps, we can recover the distance and the extinction for the globular clusters. And just to give you an idea on how much is complex the differential reddening toward the galactic globular cluster, especially those located in the galactic bulge. Here I'm reporting some differential reddening map that we recently obtained for a few globular clusters. And to give an idea of how much the situation improves applying this correction, here I'm reporting the improvement of a color magnitude diagram obtained with the HST or JWST. And by the way, here the message is that thanks to the fact that they are simple stellar population, it's quite easy to derive a very precise distance and extinction also toward very difficult regions such as the galactic bulge. And finally, we should also mention that globular clusters are collisionally systems. This means that during their lifetime, stars and binaries can interact with each other, and so they can be considered fornaxes of exotica, such as cataclysmic variable, Loma Sgr A binaries, stellar black hole binaries, and also binary millisecond pulsars. So we can now move to the second introduction of the talk that regards millisecond pulsars. The millisecond pulsars are a special class of pulsars. So what are pulsars? They are rotating neutron stars that emit periodic signal that is typical as a lighthouse. And during their lifetime, the pulsars slow down until they die. But then, if we locate this system in a binary system, we can resuscitate them thanks to the recycling scenario. And so we are in front of the millisecond pulsar subpopulation. That is the typical population hosted in globular clusters. And millisecond pulsars are characterized by very short periods, and they are very regular. So we just learned that pulsar emit a pulsating signal, but actually this is what is emitted, because what is observed at radio frequencies in the signal that arrives with the time delay depending on the frequencies. And this time delay is quantified by the dispersion measure that is defined as the free column density integrated from the server and the source. So if we have a few electrons, we have a small dispersion measure. Why? If you have several more electrons, we have a larger dispersion measure. So we can say that the more are the electrons, the larger dispersion measure. And we can also assume that if you are more distant, you have more electrons in the middle. In fact, it is commonly thought that dispersion measure is a distance indicator. In the last year, we assisted to a significant increment of detection of millisecond pulses in globular clusters, and this was mainly due to recent radios facilities such as MeerKAT, FAST, and GMRT. And we also detected a larger number of millisecond pulses in a larger number of globular clusters. So we are now ready to put these two fields together. And to perform the work that I'm going to present, we used just two publicly available compilation of parameters for globular cluster, from which we use the galactic coordinates, the distance from us, and extinction. And the compilation of millisecond pulsars also in globular clusters, from which we use the dispersion measure. So the first step was just to check if it is true that the dispersion measure is a distance indicator. And so we just plotted the dispersion measure as a function of distance. And of course, we didn't find any correlation. And this is not a surprise, because this is true that these two are correlating only if you assume that your interstellar medium is homogeneous. But since we are observing globular clusters located in a very different region of our galaxy, both the bulge and the halo, this of course is not true. And so we should also remind, of course, that exist in literature models that want to reproduce the galactic free electrons distribution in order to predict the dispersion measure. The first one is the 2001 model that includes several structures of the galaxies. Then there is a second one that is the 16 models that has been a little bit improved, and it contains several more pulsars to calibrate the model. So the next step that we performed was just to comparing the dispersion measure predicted by these two models with the values measured from radio, so the true values. And what we notice is that the 2001 model is not, the residuals is not around zero. There are some trends and also some outliers are present. The situation improved a little with the 16 models, in which they are now around zero, but some outliers are still present. Then we also estimated the predicted dispersion measure for the entire list of galactic globular clusters, and we compared the results of the two models, so even also for those clusters that do not have yet the detection of pulsars, as a function of galactic coordinates. And actually what we notice is that there is a sort of mass, especially toward the galactic center, where probably it's very hard for the models to reproduce small structures. And so, since the motivation of this work was to furnish to radio people that needs the dispersion measure to search new pulsar, was to furnish also an alternative way to the galactic models to predict the dispersion measure. So the idea was to check if there is any observable that is independent from the model that can suggest to you the dispersion measure to use. And so the idea, as a spoiler, was to use the extinction. So this was the plot before. As now, if we plot the dispersion measure as a function of the extinction, we found a very nice correlation, and it can be reproduced by a power law function. This is very interesting because it means that if you have a value of the extinction for a globular clusters, and basically you have for the entire list of globular clusters, you immediately have a first guess of dispersion measure. And so to check the advantages of our prediction with respect to the previous models, we performed the same kind of comparison. In particular, here I'm reporting the residuals of our prediction with respect to the radio measures, What we found that before we started with the large scatter, and now the scatter is decreased. Of course, it's around 0 because it's a sort of self-calibrated model. But the most important thing, in my opinion, is the fact that the scatter decreased. And also, I want to point out that here, for example, this cluster that is glimpse C01, that is a system with a very large extinction, even if it's not so far, is now well reproduced. And also comparing with respect to the galactic coordinates, the models, we noticed that comparing the 16 and the 01 toward the galactic center, they are not working well. But now comparing our prediction with the 16 model, that we noticed that was slightly better, there is less scatter. And we, however, notice that there are still some outliers. And we believe that our predictions probably may be better since are based unobservable, and so can work even if you are not able to reproduce a small structure in the models. So what's next? Forgive me if this slide is not as complete and you are more expert than me on this, but we can do next step by deriving homogeneous extinction and distance estimates. In particular, we should take into account the extinction law variation, especially toward the galactic bulge. And it would be very interesting to convert the 3D dust map into 3D dispersion measure maps and to compare the predicted dispersion measure with the true values measured from radio for the local pulsar population, or vice versa, to convert the dispersion measure in the extinction value. And then it would be interesting also to apply this method, see if the relation is still valid toward extragalactic sources. First of all, toward the Magellanic Clouds, for which some pulsars have already been detected, and so for which we already know their true value of dispersion measures. And then if it works, maybe also consider the opportunity to enlarge to other local galaxies such as M31. And then finally, also a sort of warning for fast radio burst community, because typically the dispersion measure of fast radio burst is used as a distance indicator. And this is in principle is true, but depends on if your fast radio burst is located in front or behind the host galaxy. Because I thought with a small change in distances, you may cross several more material, and so having a larger dispersion measure. And also don't forget to, of course, take into account the contribute of our galaxy. And so to conclude, we just checked that the available galactic models are not able to reproduce very well in detail some substructure, especially toward the galactic bulge. And we propose a new simple method to have a dispersion measure first guess that is very helpful to help the search of new pulsar in globular clusters that are newly investigating. And our model independent from the galactic models, and probably the conclusion that better fit the conference here is that we found a correlation between two components of the interstellar medium that have been derived just by using properties of stars, exploiting data acquired at different different wavelengths. Thank you for your attention.
Thank you so much for that talk. Do we have questions from the audience?
So yesterday, Bob Benjamin, I think, showed that the distribution of H-alpha emission, presumably indicative of ionized gas, was on the surfaces of cavities, which is presumably also the surfaces of the dust layers that you would trace with 3D dust structure. So when you do a map of 3D dust structure to try to find dispersion measure, at some level, what you're really doing is a surface versus volume move. And I'm wondering if you have any thoughts on how to appropriately offset that if you get to those sorts of fine scales.
Okay, so first of all, this is a very simple way to estimate this pressure measure, and it would be even more interesting to put some ingredients, maybe also find a relation that take into account both the distinction and the H alpha distribution. I think it would be very interesting to add also these ingredients to our prediction.
It's complicated. H alpha, of course, goes to this density squared, so it makes it complicated. Go ahead.
Yeah. So I just want to say that the model that we have that has the electron density, is available to you, so you can take it. But I was noting in my talk that it's the match with the pulsar dispersion measures was not so great. But I think after your talk, I think I understand why. And so as Mark was saying, in our model, the ionized gas comes on with layers of dust clouds. But if your thing correlates with the dust clouds, then there needs to be some level of partial ionization to give you a better agreement. So why don't we talk afterwards? But I think this is a fantastic work.
Okay,
So.
thank you.
Yeah, sorry, let me just ask then. I mean, we know that there's plenty of ions sitting inside of that are clouds. Right? There's partial ionization inside these clouds. So I would expect that you need to track that as well, which would be tracked by red, but not by your method. Is that right?
Our model doesn't, basically the Lyman-Containing photons only hit the surfaces of clouds about 0.05 parsecs.
Right.
So the rest of the cloud is neutral, but that's probably not true.
Definitely not true. Says carbon 2. Anybody else have questions? I have like 6, but I'll. Do you have any evidence that the spiral structure that is drawn in NEO1 or in the other model that you showed does anything useful?
What? Sorry?
There's spiral structure drawn in the NEO1 model and the YMV model. I didn't see the name of the other model, but there are 2 models of electron distribution. Do we know of any evidence that those spiral arms provide value? If you just azimuthally smoothed that, would you get as good a result?
I don't know, actually.
Okay. Big skeptic of arms that look like that. And so seeing that up there is
She'll be surprised. Oh,
I show one of your slides, the relation between the dispersion measure and the PV minus V at low values was non-linear. Is this true? Or?
Yeah, it's not linear, no.
Do you have an interpretation of that? Or?
No, for the moment, no. I'm still writing the paper, so if you have any comments, is welcome. I mean, here is almost linear, but probably at the.
What are those scales? It's PV minus V?
Yeah, I'm sorry. Here we have, I don't know why I forgot to add the animation here, so it's covering. Here we have the extinction. The largest value here is for glimpses is around an EB minus V around 3.85. See, this is 0.4. And of course, this plot is in a logarithmic scale now.
The main slope is 1.
Okay, I didn't report intentionally the relation here because it's still under refinement, and I prefer to remind to the paper, but it's something like power to the 0.6, but I can show you later.
If you go forward 1 slide.
Back.
There's a residuals plot you have.
Yeah, this one.
Keep going. Just stay on the right.
Yeah.
That's what I'm thinking about. That. So this is saying that the scale height is wrong.
These are the comparison between 2 models as a function of galactic longitude and latitude.
Right. And the latitude has this shape.
Yeah.
Residuals have this shape that to me looks like.
Yeah, probably if you zoom, you see something also like this, a decrease, then an increase, then a decrease again. So maybe it means that the galactic center is not well reproduced. You have some structure that is not implemented in the models, at least in the 0-1, because these features slightly disappeared when you compare our prediction with the 16.
Oh, I see. These are all basically in galactic center only. So this is going to be some feature of the thickness of galactic center.
Yeah, I think something similar, yes.
Any other questions for our speaker that are not from me? Excellent. Let's thank our speaker again.
I think how all these topics are mixing together, it's the best. Okay. All right, Sebastian. So we got a laser here. This will advance and retreat. That's going to be your timer.
Yes.
Okay, we'll set that. And then
I'll try out the laser. Okay.
Let's see here. This. Do the thing. All right.
Okay.
Take it away, Sebastian.
Hi everybody, my name is Sebastian. I will tell you today about the SGOSAN-OB association, and I want to convince everybody here that we see some kind of star formation propagation and signs of stellar feedback in this association. I've recently started as a postdoc at the CFA with Catherine Zucker, which means I'm contractually obligated to show you this dust map here. But this is a nice way of basically setting the stage of where SGOSAN lies. So if we zoom in here, for everybody who doesn't know about the SGOSAN-OB association, so we are essentially here. This is, well, I'm a little bit shaky. This is the local bubble, and SGOSAN lies here on this edge of the local bubble here. So if we look out into the night sky, SGOSAN covers a quite large area on the night sky, and it's associated with many molecular clouds that we see, many of these features that we see in the dust maps here. Here is a sample of this landmark study of Deseo in 1991, who uses Hipparcos data to essentially find SGOSAN in proper motions and positions on the sky. And you see these original, basically, cluster separations that Blau laid out in the 40s, I think, where you see here Upper Scorpius, Upper Centaurus Lupus, and the third cluster LCC. And why studying this object is very interesting to us is basically SGOSAN is the nearest large laboratory of young stars, where we cover large ranges of ages from the very young up to around 20 megayears. We basically have now access to massive stars, which essentially means it's a nice laboratory for studying star formation, planet formation, but also cluster evolution across these timescales. And since we have massive stars in this region, we also can study basically the interaction between massive stars and the ISM. However, we have studied these regions for more than 30 years, or almost 30 years. There are still open questions that we cannot really constrain observationally. And the first of which I will talk mostly in my talk today, which is, does star formation leave discernible spatial temporal patterns, or do we see basically random star formation processes which don't leave any patterns here? Another question that is slightly related is, what are the timescales associated with molecular cloud formation and star formation? This has been a little bit better constrained, I would say, but not at looking at OB associations. Another question is, what is the role of stellar feedback from massive stars in the subsequent formation of stars? And last but not least, basically, can we quantify how many stars have been formed from feedback from massive stars? So one tool that is very handy and useful in essentially answering these questions is having access to star formation history. So basically painting in here all of the ages and looking at the buildup of this association. And pre-Gaia, these maps essentially look like this from Harbich and Mamacek, where you see some kind of gradient from Upper Scorpius to LCC. But since Gaia, since we can kind of disentangle now really nicely the distance, this population in distance, there have been many studies to essentially refine this. And one very, very nice study of Ronan Kerr here, who is in the audience here, has essentially shown that there's much more complex patterns in SGOSAN that we didn't see before. However, although we have now these very nice star formation history maps of SGOSAN, Nick Wright in his PP7 report still claimed that star formation histories of these associations have so far failed to reveal these simple patterns, as you see in the sketch here, of star formation propagation, where you see kind of all kind of stars triggering, and then here these generation of new stars again triggering the next generation of stars. And I think one of the challenges here is that basically disentangling these associations is quite tricky because they disperse quite rapidly. They are not bound groups, but are quite low density over the field background. And since they have kind of formed from the same molecular cloud complex, the velocity differences are also very small. So it's very, very tough to disentangle this using our clustering methods. So the goal for my work was to basically kind of hand tailor clustering algorithms to look if we can kind of disentangle this association even better. And I will give you a quick rundown of how this works. So basically I'm using a density-based clustering algorithm, which looks at the density field. And one useful definition in clustering is basically you assign all points into a cluster if it ends up, if you follow the gradient in a local mode. A second, also very useful definition is basically you slice this density landscape, and then everything that's above and connected you call a cluster. And if you slide this level across a saddle point, you merge these two clusters. And if you do this continuously, you end up with this nice cluster graph or cluster tree. And this is very useful, but of course we don't have access to this density. We only have access to noisy estimations of our density. So we also have quite noisy gradients. So this leads typically to an over-clustering of our input space. And what we want to do is basically prune this cluster tree. So we run through, in our algorithm, we run through the maximum density saddle points from top to bottom. And at each point ask ourselves if we should merge these two clusters or not. So we merge based on a modality test. So we do some kind of spatial statistics if these two should be merged based on basically walking from one peak to another peak over this minimum energy path. And if we cannot reject the null hypothesis, we basically merge. And then we do this iteratively until we essentially generate our clustering result. So quick look at the timer. If we then apply this to the SGOSAN OB association, I will quickly show you what the results look like and then how we interpret these results. So going back to this very nice image from Gordon Edenhofer, I will now show you a cutout of the basically dust here, where SGOSAN should lie in here. And I will then fly into the dust map and show you our clustering results. So this is the cutout that I've chosen to not overwhelm you, cutting out many of the rest. So we basically fly into the dust map here. I hope nobody gets sick. And then we kind of rotate around this shell of the local bubble. And here is basically the clustering result, throwing away basically everything else that is not associated. You see that SGOSAN kind of lies very neatly in this cavity here. And you see immediately some very nice age gradients appearing, very similar to what Rowan Kerr found. And if we now kind of abstractify this with these shapes, I will tell you quickly some facts about this clustering. So we have identified some new substructure in this region. We see very, very clear spatial temporal trends emerging. and I will talk to you about this in a second. But also we see that we find groups with very, very small velocity differences in the sub-kilometer per second range, and we recover quite low number density group of 0.01 sources per cubic parsec. And all of these subgroups kind of remarkably have in itself a very, very low velocity dispersion. So if you consider this association as a whole, it has around a velocity dispersion of around 5 kilometers per second, but each individual subgroup is kind of very, very neatly co-moving with a very, very, it's a very, very cold group essentially. Since we have ages to these groups using isochron fitting, we can now kind of build up this association, or we look at basically the history of how this association was formed in age. And we see these very nice patterns emerging of these 4 bursts of star formation. So here you see it in the clusters, and here you see it in the stars. And we see basically these 4 bursts being separated out by roughly 5 million years. Since we have now the locations and these bursts, we can kind of look at where these different episodes of star formation kind of lie. So we have roughly 20 million years ago, this initial onset of star formation that generated the first generation of clusters. And then moving kind of inside out, we basically form here a huge chunk of what is Gaussian nowadays. So here we form most of the stars 50 million years ago. This constitutes many, many massive clusters, which also means massive stars. And we estimate that in here around 15 supernovae should have gone off, which aligns very nicely with what Catherine found to be the progenitor of the local bubble formation. And then as you basically move to the next generation, you are forming these very interesting sequences that kind of move outwards away from the previous generation. And this kind of ends in this most recent star formation event, which again moves kind of outwards here. If you look at this picture at once, we kind of see these very, very nice cluster chains emerging, which are 100 parsecs long. And I want to focus on this one chain today, giving you an impression of how this chain looks like. So we basically have a chain of old stars on the top here. And then if you progress down this chain, we basically see that we lose mass as a function of age. And if you look at the velocity differences between, if you sit basically in this cluster here, you have some kind of acceleration away from this initial cluster. And all of these stars move kind of downwards in the negative c direction. And we see that this acceleration here very nicely, that you basically, as you move into, if you move below the plane, you still kind of accelerate away from the plane, which goes against the restoring force of the galactic potential. So we think we see some kind of imprint of some kind of force term that's additional to the galactic potential here, which we think is feedback from the massive stars in this cluster. So this paints a very clear picture of basically star formation propagation, which already ALMA Green and Lada talked about in the 70s, where you have massive stars here, which kind of have imprint some kind of feedback onto your molecular cloud. You form stars, you use up some of this gas mass, and these stars, once they have kind of evacuated, don't feel the force anymore from these massive stars here. They might also have massive stars and push again on the next generation, accelerating these stars away, in this case, from the plane. And we even see basically the residual gas at the very end here, which is here the very nice Corona Australis molecular cloud, where you basically see here the clusters leading up to this cloud. And then in this cloud, we have this very nice cometary morphology with young stars still embedded in here. So to sum up, I think I'm 1 minute over already, so I'll make this quick. So I think we have good indication of finding some kind of inside-out formation where the older clusters in the center have kind of triggered star formation at the outskirts of this association. And you basically have a drop in mass. And when we look at the velocities, we see this imprint of feedback onto the next generation of stars. And at the very end of this, we see that we still have residual clouds that are basically shaped from feedback from these massive stars. And if you now want to attribute kind of how much stars have been formed in these chains, we see that almost half of all the stars have basically formed as a result of this feedback triggering. So thank you, and looking forward to the questions.
Thank you so much for that talk. We must have some questions from the audience, like a bunch of them.
My question is, for each subsequent propagation, the mass of the cluster is going down. If you think of this in terms of like triggering, surely it would be sweeping up more mass, and then it should be more of a consistent, the sizes should be more consistent rather than decreasing. So how is that consistent with triggering rather than just a propagation or a relocation of just the gas? So I just wanted to know.
That's a good question. So I think, so if you have just a pocket, like in a very idealized sense, if you have just one pocket of gas available and you start from one end of this gas reservoir and just basically trigger through this gas reservoir. So this is basically a picture that we're painting. Of course, in reality, you have more mass at the end or more gas at the end of this cloud. So you might run into the next chain. And I think this more or less connects what Cameron Swigan has been doing, that this is not a standalone structure that just formed out of nowhere, but this is connected to other basically cluster families that are kind of sweeping up gas and forming their own kind of association as you go along. But yeah, this disentangling basically this question is maybe not so easy just using the cluster data.
In the back, in green.
Thanks for the talk. I'm wondering, and maybe I'm expecting this wrong, but is the internal kinematics, you talked a little bit about it with the velocity dispersion and you said they're all relatively similar, but is the phase-based distribution of the subsequent clusters unique? Is that something you can use to probe this?
Unique in the sense that they are kind of separated from previous generation?
For instance, their distribution of the stars in velocity space, are they all spherical? Like, does each cluster look the same in velocity space?
More or less, yes. They seem to be all more or less Gaussian and kind of connected still to the previous generation. So if you basically build up this, sorry, if you build up this association in velocity space, you see that you basically start from a seed here, and then you don't have basically another velocity cluster up somewhere else, but you kind of start building up this velocity, I'm so sorry, this velocity distribution, kind of adding on velocities that are very, very close, which again is kind of indication that, I'm sorry, that you basically have some kind of transferal into the next generation. Yeah, and that everything is kind of connected.
Thank you. Thanks, Sebastian. Great talk. I'm just wondering about that birthiness result that you had. Do you think that that's real? Because I assume you're giving your ages based on the like bulk age across all the clusters. I would imagine there's going to be like across each of those clusters. So I wonder if you include that, it might smooth out. Do you think that would happen or not?
Yeah. So this has already been controlled for this age spread. So we are using some kind of conservative kernel here to smooth out any of the unreal substructure that we see if we just plot mean isochronal ages or something. So if you just plot mean isochronal ages, this will be much more complicated. But we have already kind of tried to correct for this uncertainty that we have in the estimation of the ages.
Right, great, thank you.
Oh, yes, hold on.
We have one online.
Great.
Lisa, you want to go ahead and unmute?
Yeah, you just read it out.
Oh, she says the hand raised.
Oh, okay, then she can read it out. She can unmute and
And Lisa, do you have a comment, question?
Sorry, I didn't hear it. So thank you very much. Fantastic talk and very interesting results. I'm wondering, about this feedback-induced star formation. Like, do you expect how much gas from the original generation of star do you expect getting to the second generation? I'm wondering if they could be, how much polluted it would be with the chemistry of the first generation, if you would expect differences like alpha element enhancement, for example, in the following generation of stars.
Yeah. So we actually tried to look into the metallicity if we see any changes in chemical composition between the initial cluster and basically the children of these clusters that we think are the children. But back when we published the study, the data didn't really seem to be informative enough to give us any indication if there seems to be any kind of metallicity gradient where you basically enhance basically the metal content as you move along the chain. But I think maybe in a few years we might have good enough measurements already with possibility to more or less constrain this chemical enrichment as you move along the chain. Was this what you were asking?
Thanks. Thank
yes,
you.
Thank you.
All right, let's thank our speaker again. Many more questions, but please do those over.
And break when that comes up after this talk. So this turns on. It's on to you. All right, place your pointer here if you want it. Yeah, slides like that. How much is at the time for you there? Yeah. Okay. So, okay. All right, Francois, take it away.
Okay, I would like to start thanking the organizers for bringing us all together here. When I saw the announcement of the conference, I thought it would be a great opportunity to present the work we were doing on the Pleiades. You see here the visible image which many of you have recognized. And I would like to mention my collaborators. 3 of them are in the room here. It's a collaboration between our institute in Paris and scientists here at Space Telescope. So the Pleiades Nebula, now a different view provided by the IRAC camera on board of Spitzer. So we are looking at the mid-infrared online with what I will show later with the James Webb. And it's a pH emission, and there are 4 of the Pleiades stars which are on this image, and I will in black as the star Meropia will be focusing on. So what is this object about? We have a cluster of stars on the Pleiades which is emitting a diffuse interstellar molecular gas at a relative velocity of 10 kilometers by second. And in this Spitzer image, there is no evidence for a Bow-shock. And so the idea here is that the stars are just shining and locally making the dust emission brighter for us to look at. So it's an opportunity very much in line with what was said yesterday about the 3D. We know the position of the stars, and as the stars are highlighting the ISM locally, we know where we are looking at, and it's a volume. It's a small volume, a few parsec in size, which is at a distance of 135 parsecs. So it's like we are having the opportunity to look at the ISM in 3D. So the radiation field is a bit enhanced, but not very much above the average value. And what is important, but that we don't have this dynamical interaction. So it just we have switched on a light to look at the ISM locally. So the scientific motivation when we applied for time and we worked on this data was say let's really use the James Webb to observe a well-characterized environment, a bit designed as a physics experiment, which will help us study interstellar turbulence on a very small scale, on a scale which we don't access usually. Our goal was to really be able to link the observations with the theory of MHD turbulence, which is a very difficult thing to do. Many studies try to do that, and it's often very frustrating to connect the observations with the theory of interstellar turbulence, and this was a main goal for us. So when you start a project like this, you wonder why many people have already studied interstellar turbulence using ISM dust observations, and you wonder why am I going to do better? And I think there are several perspectives which are new with this data, that the stars are emitting a very small volume, and so everything you see has to come from the cold ISM as the more diffuse components. They don't build up enough column density over this volume to be seen. And so you are focusing on the one phase of the ISM, and since you have the local heat source, you basically can neglect what is in front and the foreground and background emission. So we are isolating a small piece of this ISM. And with the resolution of the James Webb, we are able to reach scales which are very tiny compared to what is usually done. And basically, we are down to scales which are comparable to the size of the solar system. And at those scales, you expect interstellar turbulence to be subsonic, and so you don't have to worry about considering shocks. It might be a regime where it's much easier to bridge observations with the theory. And often what a plague in analyzing ISM observations is that turbulence gets mixed with the ISM phases transitions, so you don't really know how to take things apart. And what part of the observations may be interpreted as evidence for phase mixing, and what is really a signature of turbulence. And here we are observing scales where the time scales which are involved are much shorter than the phase transitions. And at the end, what is going to be the result of this is that we are going to show you that the energy cascade of interstellar turbulence is anisotropic. So the observations, observing such an object is kind of unusual for James Webb. It's a very big object on the sky. It's about a degree size. Here you have the visible image. You zoom in on the Spitzer image, and then with the James Webb, we are able only to observe two fields. And here this star may appear, one field which is close to the star, so we really get the effect of the illumination, and a control field which is still within the nebula but further away from the star. And those are the two images we obtain in pH emission, but we really observe these two fields in four filters, and the four filters are designed so that we can separate two tracers, the pH emission and in the near infrared, and the molecular hydrogen through its fluorescent near infrared raw vibrational lines. And why we picked these two? Because they are basically the paths are partly ionized, and as such they are connected to magnetic field lines, are tied to magnetic field lines. So we are going to use them as tracers of magnetic fields, and the molecular hydrogen is a neutral species. So the first challenge we faced analyzing this observation is that it's an amazing image. That you look at the Pleiades, and what you see first is that there are many stars and galaxies in the universe. And if you want to access the diffuse emission, which we clearly see in this image, if you want to do a statistical study, we need to get rid of this. The Merope star is here above. We need to get those the spikes, you need to get rid of all the stars in the galaxies. And this was a major challenge in the work of a PhD student, Guillaume Vigoureau, during an internship here at the Space Telescope Science Institute. And I encourage you to go and see his poster, which describes the steps to go from this image to this image, which we can actually now analyze statistically. So this is one of the images, and we selected 2 images in each field, and this is one of the images to illustrate. So you get, so here we are using basically the James Webb as a microscope, and we are looking at the ASM on very tiny scales, and the whole size of this field is 80 milliparsec. And what you see, it's very smooth, it's very regular, and it has this anisotropic structure. And you can recognize the structure, the anisotropy you could see already in the visible image on larger scales. You see it down to these small scales. And we are going to analyze this anisotropic structure through Fourier transform. But the Fourier transform, we do it 2D, and we get for each ring here, you get a profile of the power as a function of the angles. And what you see, it's anisotropic, and the first result, which a bit surprised us and it took us to understand, is its anisotropy drops as you go to smaller scales. So the next step in our data analysis was today how we are going to model this, and I'm going to explain to you the model, which is shown here in dashed lines. So for this, to build a model framework, I go back to the properties of interstellar turbulence, which we know that MHD turbulence is anisotropic, and this is a fundamental property of MHD turbulence, which dates back from this paper by Goldreich. And the idea here, which is drawn here, is that as you go to smaller scales, and the eddies become elongated along the magnetic field lines. And here it's shown as a flux tube, but it can also be a magnetic sheets. And here the idea that the magnetic field lines are aligned with these tubes. And so the correlation length along the magnetic field is much larger than across the magnetic field. And in the theory of Goldreich and Sridhar, the ratio between the length of these eddies along the magnetic field lines and perpendicular to magnetic field lines goes as this ratio, and between the driving scale of the MHD turbulence and the scale you observe perpendicular to the 1/3. And if you assume that the turbulence is driven by the interaction of the stars, the cluster of the Pleiades with the ISM, this size must be 3 parsec, and it might be larger if the turbulence is driven on larger scales, but you get very high ratios. So you are at a scale, so we are at a scale of about milliparsec, where the eddies should indeed be very elongated. So the next step is to, once we would like to use this framework of anisotropy to interpret the data, but so we have to have an analytical framework where we connect the power spectrum of an anisotropic medium in 3D to what we observe, the power spectrum of the column density. Yeah? And the mathematics to do that were developed in all papers, but always with the assumption of isotropy. And so the work we did was to extend this analytical framework to consider an anisotropic medium. And I will not go through the mathematics, but at the end, you decompose the power spectrum of density into the parallel and perpendicular modes to the magnetic field. If you use the Goldreich-Sridhar formulae, you find that the perpendicular modes are much on those scales we are observing. They are much the amplitude is much larger, so you are completely dominated by the perpendicular modes. And we really are sensitive only to structure which is perpendicular to the magnetic field, and you propagate this through the geometry, and you get this formula which we are going to use to fit the data. And this provides the angular dependence of the power, and it fits well the data. So in practice, this is an illustration of this model. So the anisotropy you observe is depends on actually it's a geometrical effect, and it depends on the orientation of the magnetic field with respect to your line of sight. And it depends, of course, on the degree of organization of the local field. And the anisotropy is with respect to the local field. If this direction of the local field varies across your sample, along the line of sight or across the sky, you lose part of this anisotropy. So you don't, the data really, the shape of the profiles tells you about the geometry of the B field. This is the result in the case where we are observing flux tubes. And if you observe magnetic sheets, it also depends on the orientation of the sheet with respect to the plane of the sky. And a nice result of this modeling is that it naturally separates the observed emission in two components. There is an anisotropic component, which is the Pleiades component, which is the pH emission from the Pleiades, and we naturally discover another component which has a much flatter spectrum, which is isotropic. And this component is very likely to be extragalactic, and because the slope of this component is close to what you expect from galaxy clustering. And so we basically had a difficulty in the data that even after cleaning of stars and galaxies, we still have an extragalactic residual, which is made of very fine sources, and we are able through this modeling to separate the two components. So when looking at very small scales in turbulence, one always expects to see a signature of the dissipation scale, and in particular the one you expect from the friction between neutral and ions. At some scales, the neutrals should decouple from ions when the scale for the frequency of available waves is equal to the neutral collision rate with ions. And it's interesting to see that this scale actually may be too small in the perpendicular direction to be observable. Here I have increased the value of the driving scale of MHD turbulence, but if it's as high as 50 parsec, and you realize due to the structures that are on those scales are very anisotropic, the eddies are very anisotropic, and the cascade in the direction which is perpendicular to the B field, and the one we can observe, becomes too small to be seen in the data. So it might be this anisotropy of interstellar turbulence, of the turbulent energy cascade, might be a reason why it has been so difficult for observers to find a signature of a break in this power law, a signature of which will be a signature of dissipation of interstellar turbulence. So I'm running late. I would like to finish with an unexpected result of our observations. We observed molecular hydrogen, and that was a curse because this is the image we got from the pipeline. It was really ugly, and we realized that it is like in the mythology, and the Pleiades sisters are being pursued by Orion, and this observation was done just after Orion, and there was a persistent pattern which Nicolas Flagier here, his students, was able to identify and correct for, and we got these clean images from after processing. And the nice thing about this is that we discovered that all this, when you zoom in and stretch the image, you see that the molecular hydrogen is revealing those filaments, which happens to be perpendicular to the main direction of the striations we see in the pHs. And the problem we are working on now is how to fit those filaments within the interpretation framework I presented to you. So this was my last slide. I will show you here the main takeaway message of my presentation. Thank you very much. Just a few questions.
The ion neutral dissipation scale doesn't dissipate Alfvén waves, transverse waves. This was already shown by Balsara in the 1990s analytically, and Jeff Oishi and I showed it numerically around 2012 or so. So even if it were within range, there's probably a smaller scale that's the actual dissipation scale.
Okay. So I would like to talk to you about this. Yeah.
Please.
Yes.
Be here all week.
Yeah.
I'm really interested in the way that you're using the of the magnetic fields here, especially because of NearCam, you're probably probing the 3.2 micron
Yes.
complex, and typically those are tracing the most neutral pods. So is there just some percentage that you believe are ionized in that 3.3 complex that would be tracing the magnetic fields?
I'm glad you asked this question because it's an important point. I think the pHs at 3.3 micron are supposed to come mostly from neutral molecules. But what is important for this dynamical coupling is that the charged state of the pHs changes over time scales of about a year. And this is much shorter than the dynamical time scales which are involved here. So basically the particles you see at one given time are neutral, but this particle will become ionized very shortly after, and they're all coupled to magnetic fields because they keep being ionized and they can never separate from the magnetic field. So that's an important aspect.
Let's thank our speaker again.
So our next speaker we have a special talk on Habitable Worlds Observatory. What did you set up?
I wasn't sure where everything was going.
Yes, let me get you that.
Good morning. Can you hear me? Is it on? Okay. It's really great to see everyone here. I want to thank the organizers for all the work that they've put into.
Three, two,
wow. Magic. All right, starting over. Really, it's great to see everybody here, and I really want to thank the organizers for all the work that they've put into bringing together the conference, bringing everyone here. It was not a small feat. And for reaching out about this talk about Habitable Worlds Observatory. Now, you might wonder, why on earth at a conference like this we are talking about a facility called the Habitable Worlds Observatory? Right? Why do we, people who study individual stars, clusters, associations, the interstellar medium, and everything in between, why do we need the Habitable Worlds Observatory? Okay, an easy official answer is that Astro 2020 said so, right? And this is not to be taken lightly because a considerable number of our esteemed colleagues, including I think some people on the SOC for this conference, led by co-chairs Fiona Harrison and Rob Kennicott, put a lot of work into determining what the priorities for astrophysics should be for this decade. And they determined from a large amount of community input, including 2 mission concept studies, LUVOR and HABEX, that HWO should be NASA Astrophysics' next flagship mission after Roman. A large infrared optical ultraviolet space telescope with high contrast imaging and spectroscopy, with the goal of searching for biosignatures from the habitable zones of exoplanets and providing a powerful new facility for general astrophysics. That means everything we do. Okay, a much easier way of thinking about this and saying it, especially for those of us who are Hubble users, is that HWO is a super Hubble. Imagine a Hubble 3 times bigger, right? With the key project. Remember why Hubble was launched in the first place? It had these key projects. This key project will be to search for life in the universe. So this is now a really outdated animation, but it's always fun to show because it compares Hubble to a Sgr A concept. And now I'll show later on what updated animations and models look like, and they are not in low Earth orbit. But in a nutshell, this is, I think, what most people want to know about what's happening with habitable worlds today. There has been, in fact, a lot of progress since the Decadal Survey report. It will be at L2, and these are just preliminary specs because the requirements have not yet been established. But the telescope is large. It'll be larger than about 6 meters. It's going to be a UV optical near-infrared telescope, spanning from 1,000 angstroms to about, HK band. It will have a coronagraph, which will do high contrast imaging, blocking out 1 in 10 billion. It's only going to leave 1 in 10 billion photons so that we can directly image the planet around sun-like stars. Then we have our workhorse instruments, right? Things that we're used to, like WIF-C3 or NIRCam, and with a UV multi-object spectrograph. And that will really be revolutionary. I imagine that the way we can do multi-object spectroscopy from space in the infrared, but now in the ultraviolet. There's also another instrument bay, and the 4th instrument is still to be defined, but some candidates include a near UV coronagraph, a far UV IFU, and a UV spectropolarimeter. Okay, now these are the more updated versions of the models that show the deployment architectures, one with web-like wings. Before, you didn't see something to protect the observatory from micrometeoroids, but in these models you do. So you see the barrel unfolding here on the top. On the bottom, there's a Roman-like hard barrel with this camping cup deployment that just went away. But all of these models that are being studied, they need to fit into the fairings of upcoming heavy lift capabilities such as SLS, SpaceX Starship, and Blue Origin's New Glenn. And for more details on some of the technical aspects of the mission, you can check out this QR code. Lee Feinberg, who is the principal architect of HWO, just gave a talk to update everything on the mission just a couple days ago. I think one of the aspects that captures the imagination really is the fact that people are designing the mission to be compatible with servicing. Imagine that, servicing, not in LEO, at L2, robotic servicing. So what this buys us is that, like Hubble, we can have multiple generations of instruments, right? It'll also potentially allow for earlier launch date, because then we can just focus on the minimum needs and then, improve the capabilities as we go along. And then, believe it or not, it actually makes a lot of sense to think about making or designing the observatory to be compatible, because you then design it to be modular. And that helps with integration and testing. All right, so in the search for Earth 2.0, we're going to be looking for Earth-like planets around sun-like stars, right? Here on the HR diagram. But a lot of people here, we know that in order to create these rocky planets, to seed life, where do those elements come from? Not necessarily here, but here, right? It's the massive stars. The massive stars are the engines of heavy element production that are needed for life, right? And this is the way our work ties into this grander story of our origins. Without the things that we study in terms of star formation, massive star formation, we will not understand how life came to be. Not only that, but of course, in a lot of the talks, we're thinking about how the massive stars, the stellar feedback, those supernova explosions, the stellar winds, the radiation pressures, give rise to this incredible structure that we see in the ISM, and to these beautiful pictures of the dust emission taken by JWST. On the grandest scales, this is how life is seeded through those massive stars and that feedback. And so how does this connect to why we need Habitable Worlds Observatory? Of course, massive stars are extremely hot, right? The bar UV indicators are a very standard way of measuring the star formation rate in the greater universe. Their SEDs peak in the UV, but not only that, they're so hot, and I think most people in the audience know this, all of the features end up in the UV. For studying the energy deposition, for studying those winds. And so we really need capabilities going down to about 1,000 angstroms in order to study those massive stars. Not only do we need the sensitivity in the UV, we need that resolution, right? And those of us who try to step out of the Milky Way, step beyond the local group to study the things that a lot of the people in this audience study in detail at larger distances, and I'm looking to my research group who is sitting over there, we know that high resolution space-based observations are absolutely critical, right? We see this, Westerlund 2, in all its glory, all this resolution. What happens when we start to step out? I mean, we sort of know this in our heads, but when we get out to 20 megaparsecs, right, and this is the distance where most of the FANGs galaxies reside, that beautiful image of Westerlund 2 ends up looking like this with Hubble. Okay, each one of these postage stamps is the brightest star cluster in 38 FANGs galaxies. These postage stamps subtend about 50 to 270 parsecs each, right? It's barely resolved at these distances. And even with the inventory that we've done, where we've amassed 100,000 star clusters, if we want to study the most massive ones, we know that they're really rare in the present day universe. So even going out to 20 megaparsecs isn't enough, right? The mass function is a power law of -2. If we have 100,000, how many does that leave us of things that could be progenitors of globular clusters, 10 to the 5 solar masses and up, right? Hundreds. Not enough to do statistical analyses, even going out that far. So yes, we do need a much larger Hubble. So I'm going to show one Pathfinder science case, and I'm going to talk a little bit about programmatics to bring everybody up to speed on what's been going on. But I'm talking about 20 megaparsecs not only because of FANGs, but also because if we want to understand massive stars at the lowest metallicities, which are absolutely critical for understanding all that nonsense that is going on at the high redshift universe, right? We need to get to 20 megaparsecs and resolve those stars. We do not have UV spectroscopy of individual massive stars at 1/50th solar metallicity yet. We do not. We don't have the models for those that are based on really robust observations. 1 Zwicky 18, which is one of the lowest metallicity galaxies, actually, it's the closest one, is at 18 megaparsecs. And look what happens to NGC 346 with HST at 19 megaparsecs, with 15 milliarc seconds, 10 milliarc seconds, and 5 milliarc seconds resolution, right? In order to understand star formation, high redshift universe, the seeding of metals, that give rise to life. We need to be able to resolve those stars and do UV spectroscopy at this distance in this galaxy, because that is what nature has given us. This is the bind that we're in. And this is an amazing science case led by Peters and Chia, perhaps some other people in this audience. This was done as part of the evolution of the elements working group, one of the 4 science working groups in the Habitable Worlds Observatory community science effort, where we're trying to trace the rise of the elements and molecules by studying the formation, distribution, and evolution of stars and the interstellar medium, things that are close to our hearts in this audience. So we cover star formation on the ISM, stellar population and evolution, and the cosmic explosions that seed all these metals into the ISM. I'm not going to read through this. This is an eye chart, but this is to say that there are so many science cases that have been developed over the last year and a half to inform the requirements for Habitable Worlds Observatory. And we, right now, are working on making these 70 science cases available to all of you, to the entire community, for opt-in for signatories and to provide comments to the authors. And that should happen in the next week or so. And so you should be able to understand, go in and see all the exciting science and then even contribute to those science cases starting in the next week. These science working groups have been active over the last year and a half. A new community science and instrument team is now being stood up that will be active until the end of the decade. And that announcement should be out in the next week or two. And then, so the structure, the programmatics of how we're going to get to the requirements for the observatory are changing. And so there's just been, especially in this moment of time, it's super encouraging that there's been so much support and interest and excitement for continuing and making sure that this observatory actually happens. It's the next natural step in our exploration. For this conference that we're hosting at the end of July, you can find more information in the QR code here. It's been crazy. It's like 500 abstracts received. We're trying to cram in as much as possible across, from industry to scientific research, spanning all of astrophysics and exoplanets, spanning the space economy, trying to understand how this will fit into our new world. We're going to try to touch all those key points and make a solid case for Habitable Worlds Observatory at the end of July in Washington, D.C. So at the beginning of the talk, I asked, why do we need Habitable Worlds Observatory? And I sort of gave a cop-out answer, right? It's because Astro 2020 said so. This is another way for me to think about why we need Habitable Worlds Observatory. This is NGC 628's JWST imaging of the dust emission. What do we see when we look at this image? We see all these things, right? Wow, there are a lot of bubbles. Can we explain the feedback? Can we explain propagating star formation? PAHs, there are PAHs everywhere, right? Dust. We're looking to measure the earliest phases of star formation, those YSOs. Look at that beautiful spiral structure. That's what we see. We see the stars. We see all the processes over a huge range of scales that drive, that regulate, that extinguish star formation, that result in this extraordinary structure. But the question is, when we get out of our local bubble, what do they see? As astronomers, as researchers, we do tend to exist in our own local bubble. What does the rest of the world, the public, the people who don't follow turbulence and magnetic fields, what do they see? And I think the public, and interacting with the public over the last year and a half, has taught me a lot about this and why we need Habitable Worlds Observatory. The beginning of last year, we did a press and data release for our inventory of 100,000 clusters and associations. And we also provided all the data and these beautiful images created by our very, very talented graphic artists at OPO in our Office of Public Outreach. And I think our team was just, we were taken aback at how much attention this got, because, you know, we're not breaking any boundaries, so to speak. We didn't discover the highest redshift thing, the biggest, the baddest, the furthest. No, you know, these are galaxies that we've known and studied for a century almost. So why is there all this interest? We ended up on the evening news. What do other people see? They see in these galaxies that we're trying to study how the star formation of these structures result, they see not alone. They see that there are places that are nice to look at and humans will never get to. And so this, I think, is another way of thinking about why we need Habitable Worlds Observatory. This is how we, in the work that we do, tie into our origin story. So I'm up on time, but I just want to end on a note on science. What's the intersection? How do we harness the intersection? That is the title of this conference, but not only with the interstellar medium, with stars, but with those two things and life. Those postage stamps I showed you, 50 to 150 megaparsecs, we won't be able to look for biosignatures with Habitable Worlds Observatory outside those volumes, right? It's within a tiny, tiny volume that we're going to be looking for biosignatures to be doing that high contrast imaging and directly imaging those planets. We're only beginning to think about how galactic environments, how star formation, and those very violent environments, the feedback, how they actually affect. We study how they affect star formation. We don't necessarily study how they affect the formation of planetary disks and the formation of planets. We're only beginning to understand how planets and planetary disks are formed or not formed in very violent environments, for example, at cosmic noon. People are only starting to think about that. So I think I'll end there. I think this is an area that is at the intersection that is really ripe for this group of people to think about. And I'll end there. Thank you.
We have time for about -5 questions, so I will not call for questions now. Janice will be around for the break. Okay, we'll have a break. We're gonna have our poster flash session now. Janice will be around to chat after the break. Thank you, Janice.
Mm-hmm.
All right, we have our, yeah, go for it.
Okay, we're gonna have our poster flash session.
Yes, of course.
So our
Yes.
poster flash session is, oh, I'm really bad at pronouncing names. I don't know if I can call out. Come on down and line up. And as you load them, I just have a few announcements to make before we go into our morning break and poster session. So first, if there's a sign on one of the posters to not change it during the poster session, please leave the poster up so people have an opportunity to give their poster spiel to everyone and have like their time for their session. When you walk into the cafeteria, the screen on the right, that one you can flip through to your heart's content. During the other breaks, you can also flip through just during the dedicated poster session time. Also, please keep your physical posters up on the wall throughout the week so people can browse through them even if your session time is done. And lastly, during this morning break, it is your last chance to vote on discussion that we'll be having this afternoon. So please put some tallies up on the board of which questions you want to talk about this afternoon. All right, take it away, Steve.
All right, we're gonna start with Savannah. Yeah.
Hello, everyone. My name is Savannah Gramsey. I'm a graduate student working at the University of Florida. This week, I'm presenting a poster on this star-forming filament in the 3 kiloparsec arm. Because it is between us and the galactic center, it's backlit by thousands of stars, which allowed me to make a really high-resolution extinction map of this filament. In addition, our JWST observations included a filter F466N, which is heavily impacted by a CO ice feature, which by modeling the impact of the ice on that filter, I was able to measure the ice column density toward every single star that's behind the filament and create a CO ice column density map of the filament itself. By also expanding that CO ice measurements to other clouds that are elsewhere in the JWST field of view, I was able to find out that the relationship between extinction and CO ice for the filament in the disk of the galaxy and the clouds in the central molecular zone in the center of the galaxy is different, which possibly traces metallicity differences between these clouds.
All right, next we'll have Guillaume. Take it away.
Okay, so I'm Guillaume. So the goal of our project was to characterize statistically the dust emission seen by Webb in the Pleiades. But as you can see on the original mosaic, there are not only dust, there are also stars, galaxies, and spikes. So I had first to make 3 different algorithms to remove those 3 components to finally obtain the clean mosaic. So on that clean mosaic, we can work and we can extract some statistical analysis. So in the middle, you can see the power spectrum. So the blue one is the original one, and the red one is the one of the cleaned mosaics. And so you can see that at some scale, I removed up to 4 orders of magnitude of contamination. And so with that clean mosaic, we were able to extract 4 main results. So first, depending on the field you are looking at, the power law indices will change. Then that each field is following power laws with no breaks. Then that the strong anisotropies that you can see on large scale is still there up to the smallest scale reachable by Webb. And finally, that we were also able to extract a residual component, which is due to the extragalactic emission that we can't see by eyes. So thank you.
All right, next we'll have Jordan.
Hello, my name is Jordan Bartlett. I'm a grad student at the University of Wyoming. Sorry, this is a little hard to see, but my poster is called Polarization and Reddening of Dust and Magnetic Structures in 3 Dimensions towards Zeta Ophiuchi. We saw a lot of really cool talks and posters yesterday about 3-dimensional dust maps. Those are on much larger scales than what my project is. Mine is more limited in angular distance, or angular scale and distance. But we combine optical starlight polarization, reddening, and Gaia parallax distances to examine the structures of the magnetic field and the dust over this limited area. If you want to talk to me about it more, I have an e-poster out in the back, and I would love to discuss it with you. Thanks.
Next, you'll have Yasir.
Hi there. My name is Yasir Abdul Qadir. I'm a PhD student at University of Turku, Finland. My poster is about interstellar polarization in the open cluster of NGC 7380. What we basically do is that we observe binary star systems, O-type binary star systems, using polarimeter, and then we study phase-locked variation Stokes Q and U to determine the orbital parameters. But when we observe the polarization, it is not just intrinsic polarization, but it has a component of interstellar polarization due to interstellar dust and instrumental polarization. To account for instrumental polarization, we observe zero polarized standard stars, but to account for interstellar polarization, we observe field stars. And in this case, we observed more than a dozen field stars in the open cluster of NGC 7380. We can see the degree of polarization and the angle are quite uniform. So dust is pretty uniform along the line of sight in this case. But then I had a new, later on, earlier this year, I published another paper where I observed another cluster, but that was totally the opposite to the first one. And if you would like to know more about it, I have my e-poster. Please come talk to me. Thank you.
And last but not least, we have Robert.
Definitely not least. I'm Rob Goodermuth. I'm UMass Amherst research faculty. My poster is on constraining the star-forming past, present really, and future of the Monarch 2 giant molecular cloud. This is really an agglomeration of several projects that my students and young postdoc have been working on to basically build up a means of characterizing the star formation history in embedded star forming clouds like this. So imagine an analysis similar to Sebastian's talk with less detail and crummier data, because we're looking at a more distant cloud. We're looking at higher extinctions, and we're still able to do amazing things, even though we're kind of digging into the real bottoms of Gaia's ability to detect things. But with a data-driven approach, we can find over 1,000 members, including diskless objects that performs similar to what Chandra can do inside the clusters alone. In addition, we're of course bringing together our Spitzer results over the past several years, disks, protostars, and using another machine learning algorithm, we can map the radiative feedback strength throughout the cloud and characterize the next generation of stars that are going to be formed using the cores that we find with millimeter wave surveys. Just a bonus, there's a bit of Toltec data, our next generation camera for the Large Millimeter Telescope, still in commissioning, but we've got some cool things for the Serpent South cluster on there, just a little thing in the bottom corner if anyone wants to see it. Thanks.
All right, that's our break. We'll be back here in 30 minutes to continue the session.